Good afternoon, and welcome to today's webinar put on by UAS Magazine, part of our webinar series, sponsored by TELEDYNE Imaging. Today's webinar is titled Advancements in Aerial Imaging, Multispectral, Multisensor UAV Payloads for Agriculture, Infrastructure, and Geospatial Mapping. Today we have Danny Longville with us, and he is the Vice President of Sales at TELEDYNE Luminera. And this is our third installment of this webinar series with Danny. And each webinar that we do, if you have been on other webinars, he does have new information and new things that evolve with as you know, technology and the company is evolving. He is sharing that information with you. So if you have been on one in the past, be sure to pay attention. He's got some new information that he will be sharing. So again, we thank you for being here. And with that, I'm going to hand it over to Danny. Danny.
Thank you, John. Thank you so much for the kind introduction. I'd like to start actually by giving a bit of background about TELEDYNE, just so that you understand how we are involved in aerial imaging and where this expertise is coming from. TELEDYNE actually is a big corporation, and within that big corporation, you have this group called TELEDYNE Digital Imaging. This group by itself is more than $1 billion a year, and actually, I should probably update that number very soon because we did an acquisition recently. We acquired a company named FLIR, and they'll be part also of TELEDYNE Digital Imaging. And I think the next financial reports will be included our numbers. I'm going to have something updated very soon on that topic. We're active in all kinds of different markets, not only aerial imaging, but we do a lot of industrial imaging, machine vision type of thing. We do medical and life sciences, a lot of aerospace and defense, where you could see some connection as well with aerial imaging, geospatial, obviously, even semiconductors, electronics. So a lot of diversified imaging, a lot of expertise within our company. And I can easily say that we're probably the largest player when it comes to digital imaging, the largest player in the world, basically. If I look quickly at a subset of our technologies, if I look at the camera side of things, we have a full collection of cameras, starting with the sensors. We even have the ability within our company to do sensors with a group called E2V. Which we can customize. Often we do that for our imaging. We customize a bit some of the capabilities of the sensors itself. We do cameras, either larger cameras, full body cameras, fully enclosed cameras, but also board level cameras that can easily be integrated within another subsystems and that have the benefit of being small and low power, which again can be a great benefit for some aerial imaging applications. And we even do frame grabbers, so boards that connect to a PC that you can use to connect to your camera front end, basically. There's different interfaces we offer. There's multiple different ways to connect cameras to a host systems. Could be GIGI, could be USB, or to a frame grabber of some sort. Imaging itself for us is quite wide. We do visible, which is often what most people think about when you think about a camera. But we also do NIR, we do thermal, we do 3D imaging. So we do a lot of different things, which means that we're exposed to all kinds of different requirements, all kinds of different applications, and we're happy to share that expertise, which is what I'm going to be doing with the presentation today. So today at first, I'm going to be talking about the advancement in sensors themselves, so in cameras. Under that topic, I'm going to talk about high resolution imaging, so visible camera in that case. I'm going to spend more time actually on multispectral imaging because that's an important topic. I'm also going to talk about thermal cameras. After that, we'll get into key trends. It can be technology trends, it can be application trends, so what's new, what's happening. Out of that, one of those trends would be AI. Which is, I think, important to spend a bit more time on. So I'm going to have a topic specific to AI, artificial intelligence, right after that. And just to put all of that into context, we're going to get into a case study about NDVI, Normalized Difference Vegetation Index. The case study is real. It's about real things that we're doing. It's not hypothetical. I'm going to talk about real applications. So let's start. Let's start with the high resolution imaging side of things. And what are some of the new things? High resolutions really keeps coming up. Pixel keeps getting smaller, so you can put more pixels on a sensor on a wafer. We're seeing now camera resolution of 50 plus megapixel, even 100 megapixel actually. Not so long ago, I think that just a few years ago, for us to work at something like 20 to 30 megapixel was already very high resolutions, and we're tripling that now. So things are moving quickly. The reason behind that actually is all the advancement in semiconductors and wafer technologies, all the things that people do for cell phone type of things or consumer electronics, where you do need the high capabilities, the high performance. So all of that is driving technologies for semiconductors, which find its way into camera technologies, into sensor technologies, and which allow us to really like increase dramatically capabilities in a very short window. Like I said, in just a few years, we went from 25 megapixel to almost 100 megapixel. When I talk about resolution, though, the other thing to keep in mind, it's also the type of shutter that these cameras use. So in this case, when I'm talking about 50 plus megapixel, I'm talking about global shutter cameras. I should probably take a minute or two to explain what is a global shutter cameras versus a rolling shutter cameras. A rolling shutter cameras, it's for each line in your image, each line is scanned one at a time. So if there's movement like there is in aerial imaging, when you scan the first line, the second line, the scene has changed a bit and it keeps changing all the time because you're moving. So at the end with your rolling shutter camera, your image is going to be distorted a bit. That's why you want to have a global shutter so that you basically capture one snapshot of the full scene in an instant moment. This has been more difficult to do. It did need more transistors for each pixel. So the resolution for global shutter has always been more limited than rolling shutter. So you could see these bigger numbers and think, oh yeah, I've seen like 50 megapixel a few years back. Yeah, possibly, but most likely it was rolling shutter, which is not quite suitable for most aerial imaging application. So in our case, that's a new thing, that type of resolution capabilities. Those camera tends to be a bit larger. Typically, they tend what you call 35 millimeter cameras, maybe even a medium-sized cameras. So it's sizable. It's about the size of a consumer DSLR cameras, basically. But even smaller cameras now are pushing the limits when it comes to resolutions. So if you look at a smaller camera to fit on a smaller platform, you can probably get a 1-inch type of camera at 20 megapixel now. So there too, there's big improvement, driven again by the same technologies, just driven by pixel getting smaller, basically. The thing I still run into quite frequently when it comes to cameras and imaging is the comparison with DSLR. And often those are still the reference, but the technology is quite different. When you look with the DSLR, especially more traditional DSLR, because that's changing too with the mirrorless cameras. But back when you had a mirror, you actually had a mechanical shutter within DSLR. So it's mechanical. It means susceptible to vibration. It can get damaged over time. Versus electronics, which is basically infinite life cycle, it seems at times. So DSLR did have that issue of being reliable over time. The other difference is the ease of use with the machine vision cameras, like the ones I'm talking about. Those are designed to be interfaced with the host computers. Again, it could be done through different interfaces, but it's plug and play, and you have full access to all the features of the camera itself. It comes with a software API. You can control everything. You can transfer things easily. Not always the case with a DSLR. Often in a system, you would have, after a mission, you would have to maybe uninstall, maybe open up the DSLR, take out the SD card, bring that to host computers. So the process is quite cumbersome to do. It's only getting easier with machine vision cameras because of the progress on interface technologies, which I'm going to get into at the end of the slide. So that's another key difference between DSLR and machine vision cameras. And finally, the other difference is just the filter technologies. In a DSLR, it does come with filters built in, designed basically for consumer photography, which can be different at times from aerial imaging. In a DSLR, you would have some filter, for example, for anti-aliasing. These anti-aliasing filter allow you now to take an image of an image with a scene with a pattern in there and eliminate what's called the moiré. And actually, if you look at that picture in the slide, if you see that rainbow effect on the sensor itself, that's the type of things that you see when you get aliasing. So the way to reduce that is to reduce the resolution of the scene before it hits the sensor. So you're actually blurring the image to eliminate that effect. So you lose resolution. So by definition, with a DSLR, a consumer DSLR, there's a sensor resolution specified. Your actual resolution is less than that. It's probably less than that by maybe 20 to 30% less than that. So if it says 24 megapixel, in reality, it's going to be closer to 18 or 19 megapixel. While with the machine vision cameras, you don't have that. You don't get these filters and anti-aliasing forced on you. You could put one if you wanted to, but you don't have to, which means you get the full resolution of the sensor itself. And because in aerial imaging, you're outdoor, you never end up with that type of patterns that you would see in some other applications. So you never actually face a situation where aliasing becomes a problem. So why not enjoy the full capability of the sensor itself? I haven't seen people take a DSLR and actually go in and by hand remove that anti-aliasing filter, which is, you have to be brave. You can actually damage the camera as you do this. Those are not cheap. So it's a bit of a gamble, but it's possible. Some people do that. It's a lot easier to just buy a machine vision camera. Finally, when it comes to high-res imaging, one factor that is often neglected is the optics, the lens side of things. And you get sensor technology evolving at a given pace, and sometimes the optics is struggling a bit to catch up. Often when it comes to optics, you're really limited by the laws of physics, so it's a bit harder to do. It also can be very pricey, becomes very niche, actually. So what I'm talking about is that the actual ability of the optics to resolve the scene to the same resolution of the sensor, the cameras do not match. You might have a camera which is, let's say, 15 megapixel, but the lens will not give you that resolution. It's going to give you only 30 because it's just not able to handle that. So you have to be sure that you match that. That if you get a higher res cameras, you're going to have to spend a bit more on the optics to get something that matches the ability of your cameras, because otherwise you just don't need that type of cameras, basically. In some extreme cases, I was talking about some cameras now reaching 100 megapixel. I think the optics, for some cases, you might have to get into custom design optics for that sort of things. But they will catch up. I think the lens manufacturer will catch up maybe in a year or two from now. The other improvement is dynamic range. It's always a big topic. People see actually what their phone can do now. Say, oh, on my phone I can do all these things. How come I cannot do that with my cameras? A phone often does that by combining multiple images. When you press the button to take an image, it actually takes multiple images, maybe 3, 4, or even 5. In the old days, it was 2, but it increased with processing capabilities and these things and algorithms too. So the phone will take a lot of images at different exposure time. It will then recombine those to create an high dynamic range image, and this is what now we're used to. We see this, or I'd like to get that of my aerial imaging systems. The problem with that, though, is that aerial imaging is different. You're flying something, you're moving, you're capturing scene as you're moving along. So if you're going to try to take multiple images, well, the scene is going to evolve a bit from one image to the next. So you're going to introduce some blur. You can still do it. You can still capture multiple images and think they're close enough and recombine them after the fact. But really, you're going to see some blur in your image. The edges won't be so sharp. So that's a problem for aerial imaging. So to use the same technique used on a phone is not quite appropriate for this application. There's now other ways, though, to do HDR features. You can do it with multiple gains. So instead of collecting multiple images, you collect one image, but as you collect that one image, it goes through different paths within the camera, one path being a high gain and one path being a low gain. So the benefits now is that you do one scene capture one time. So you avoid that effect I was talking about blurring. Instead, though, is that you become limited by your gain. When you gain something too much, you introduce noise in the image. So there too, you have limitations in that technique. However, it's still more suitable for aerial imaging than what would be a multi-exposure HDR mode. Low system noise, I was talking about noise when you capture something with high gain. Things are improving, though. That's one thing that when you design new sensors, that you keep pushing the limits all the time, and system noise is one of those things that keeps getting better and better and better. This one too, though, you have to look at how much are you willing to spend. You could get technology that could be a bit better, but a lot more expensive to achieve that. So you have to decide, what's the ideal solution for you, looking at performance versus price at the end of the day. One of the new technologies, and that we see more and more now, is backside illuminated sensors. That has a big impact on actually being able to work in low light and low noise. And if I explain that quickly, so historically speaking, cameras are front side illuminated. What does that mean? It's right at the wafer level, actually. So if you look at a sensor at the wafer level, you see a bunch of dots. Those are the pixels. And around the pixel, you have metal lines bringing signal from one place to the next. You have amplifier designed too. So in the pixel design, you have a portion of it which captures light, but you also have all the electronics around it. So all the amplifying circuitry, the A to D converters, all these things also need to share space with the sensing element of the pixel. So if you're going to look at the pixel design, you may find that maybe half of it is used to actually capture light, and the other half is used just for electronics, transistors, amplifiers, and things like this. That's a typical front-side illuminated camera. With the backside illuminated, what happened there is that you put all the sensing, the light sensing material at the back of the wafer. So all your electronics, all the amplifiers, the transistors, the lines, the connections, the wires, all these things stay at the front, but you put the sensing material at the back. And now, because there's nothing else at the back, the full surface can be used to capture light. So you don't lose anything. You really capture every single photon coming in. There was some other ways to do that before with lenses, and you would focus things on the sensing element, but it does include, it doesn't introduce degradations, it has limitation, much better with backside eliminated. So this is a brand new technology. It was niche before, but now it's finding its way into more and more products. So that's something to be aware of, because it's really helping. It's making a big difference. And finally, the image correction you can do to lower the noise. There's a stat I read somewhere, I don't remember when, that was talking about the evolution of cameras over time. And the stat was saying that, what was the number again? Like over 5 years, the performance of cameras when it comes to image quality, working in low light and things like this, the performance of cameras improved by 10 times over 5 years. So wow, that's fantastic. If you look at the details of it though, the sensor technology only improved by a factor of 2 over that period of time. The factor of 5 just comes from better algorithms to correct the image, to remove the noise, to better correct the colors, all these things, to sharpen the image. So there's been a lot of progress on the software side of things, more than on the hardware side of things. A bit of both, but mostly on the software side of things. So this is where the image correction techniques are very important. And finally, when it comes to high-res imaging, the camera interface, that too keeps evolving in some very interesting ways, actually. Even myself, like probably last year when I was talking about that sort of things, I would have been talking about USB 3, I would have been talking about GIGI. So USB 3 is very convenient because you can easily connect to a host. Could be a processor board, even a GPU board, one of these NVIDIA boards through USB 3. You limit the distance a bit, like 10 to 15 meters, but anyway, everything is co-located. And you would normally have multiple USB ports on the board, so you can build a multi-camera systems, very easy to do. However, if you had a distance problem, let's say you run a bigger aircraft, and the cameras at the front, the processing elements are further back, it doesn't take long before you run out of cable on USB. So GIGI becomes a better choice. But GIGI is slow. GIGI is much slower than USB by almost a factor of 4. So that's what I've been talking about. Well, things have changed now in good ways. So one of the ways is that GIGI itself, you can get faster version of GIGI. You can have 5, you could get 10 actually in the past, but 10 wasn't quite suitable. It's very power hungry, it's huge, it has big drivers, so it wasn't quite suitable for aerial imaging. But 5 GIGI is a compromise. With 5 GIGI, you get about the same speed as you get with USB 3, so almost like 5 gigabit per second, let's say, which is the physical speed. But you also get a distance at the same time. So you get a bit the best of both worlds in between USB 3 and GIGI with 5 GIGI. That's a very recent thing. It's still finding its way into different products. So yeah, you see more and more cameras now supporting 5 GIGI. The next thing you have to worry about though are the hosts, so the computers. If you need some switch equipment, the switches, you have to get the right switches and all these things. Once you go 5 GIGI though, it's all compatible. So you can connect a GIGI camera into a 5 GIGI infrastructures. It's all gonna work fine, be it at 1 GIGI speed, but it's all gonna work fine. So 5 GIGI we found actually good traction in aerial imaging right now for those type of applications where there was a need for distance and speed at the same time. I even had customers trying to use extender on USB 3. Small boxes basically that boost the signal or maybe even make it optical to go further. It's one more piece of equipment. It turns out it's not so reliable. It didn't work out too well. So 5 GIGI is actually a better choice. The other new technology that is worth talking about is coax express. So why coax express? So It's fast, even faster than 5 gig actually. It does have one drawback. It's not quite an embedded type of solutions. You need a frame grabber card. You need to be able to put a frame grabber card, so a capture card, into a host computers, and that capture card is going to have on it coax connectors to connect to your cameras and transfer data between the two. So that connector, that cable is a coax cable. That's why it's called coax express. The good thing about this that we discovered is that when it comes to connecting equipment through a gimbals where it's rotating, a lot easier to work with a coax cable than it is to work with a Gigi cable, or USB cable is even worse. So coax express actually does solve that problem. You can connect a camera now at high speed, long distance, to one of these gimbal very easily. The problem though, like I said, is the capture card. So if your application has that sort of needs and has a host computers where you can put one of those coax express capture card, that's a good solution that's worth looking at. So that's the update on high-res imaging. And I'm going to move on next to multispectral imaging. When it comes to multispectral imaging, I'm going to take a bit of time to just explain it at first, because it might be new to some people. Obviously, everybody knows about cameras and high-res cameras. It's video, like everybody's seen video before. With multispectral imaging is different a bit because we're not looking at what your eyes can see. We're looking at things that your eye cannot see. So it's like, what does that mean? And we're seeing more and more of that too. If I look a bit at what happened over a video, like the first TVs were black and white, mono, went to color with the big introduction. 3D was something that maybe less in the consumer domain, but we see a lot in the industrial domain. And multispectral is the next step of when it comes to the evolution of video. It has application in aerial imaging, but it's not limited to aerial imaging. It has industrial applications, there's agriculture applications, there's a lot of different applications. So what is multispectral imaging? So when you think of imaging, now you have to forget about imaging. You're not looking at images anymore. You're looking at a spectrum. This is what that diagram is. It's a spectrum. So this is the world now. When you talk about multispectral imaging, this is the world you live in too. A spectrum with waves at different frequency. You can see the area in the middle, the grayed out area in the middle. Right in the middle, you get the visible light from 400 to 700 nanometers. Just below that, you get UV light, and then you get into X-rays and stuff. But at the other side of it, you get into NIR, then microwave radar and thermal sits somewhere there too. Multispectral imaging lives in that block there between UV, visible, and NIR imaging. So when you do multispectral imaging, again, like I said, you don't look at an image anymore. What you look at, it's basically measurements. You do specific measurements. You don't look at the full image. For each given pixel, you make a measurement of how this pixel is responding at a given wavelength. And you may have more or less number of pixels like this, so you may have more or less number of wavelengths that you're looking at. I think in that example, I'm looking about 10 of those, I guess, I don't know. So each one of these bands in there, I make a measurement at each one of these bands. And then we combine that into a colorized image. So if you look at the pairs, you get on the left, you get the real one that you see with your eyes and with the normal cameras. And the other one is actually the colorized version of my multispectral imaging exercise. So I've taken measurements at these different points, we combine them, and this is what I'm looking at. So I'm looking at those pairs now in a totally different way. Really what I'm trying to do, I'm trying to get information that I wouldn't be able to get with my eyes. The pair reacts differently a different wavelength because of how it's made. Like all the chemicals inside the pair, its structure, its cell structures respond differently to different frequency. So I want to identify these frequencies where it responds differently, and this is what I'm going to capture, and this is what I'm going to be looking at. So in this case, I can actually see, which my eyes couldn't see, that within the pair itself, there's some imperfection. So this is a pair that looks just fine now, but it's probably just about to turn bad pretty soon. This is at least what my multispectral image is telling me. People sometimes confuse multispectral and hyperspectral, so I just wanted to highlight that quickly to clarify the difference. With a multispectral, just like my exercise before, I look at a small number of bands within the spectrum, and with that small number of bands, I look specifically at wavelengths that are of interest to me, that I know that will tell me information that I can use. With hyperspectral, I collect the whole thing. Basically, I'm trying to capture the entire spectral with hyperspectral, so a lot more information. So multispectral will depend on your application. Could be as low as 2 bands. I've seen like up to 32 sometimes, but with hyperspectral, you capture everything. So it's hundreds of bands that you're actually capturing with hyperspectral imaging. So that's a big difference. And what it means is that if you say, no, I need to do hyperspectral imaging, that's a lot of information. It's really cumbersome to collect, manage, and analyze that type of information. And it might not be useful too. It's not something often that is quite suitable for real-time analysis. You're going to collect the hyperspectral signature, load it on your supercomputer, and do whatever analysis you want to do. But if you're building a real-time systems, there's just too much. Or also, it might not be needed, like I said. I was able to do quite well looking at the pairs above just by looking at a few bands. I didn't have to look at the full spectrum. So this is where multispectral imaging comes in. Real-time applications, very application specific. You're looking for something specific. You know what you're chasing. You know how it's going to work. This is where multispectral imaging comes in. How do you do multispectral imaging? There's different ways to do that. Not all these ways are suitable for real imaging, but just to look at the technologies, you can do it with actually filters on the sensor itself, which should be on the left. You would see now that I've broken down this sensor to a number of square areas, each of them capturing a different wavelength. Or I could do it with illumination. I could use which is the second one. I could use this a mono camera and just illuminate the scene with a wavelength that I want to capture. And I just rotate through the different lights one by one. Obviously, I cannot do that for real imaging. The other two solutions are variation of that. Either it's within the camera itself, and because it's really complex that integrate all these things in one big box, or it could be with a filter wheel. So filter wheel, same idea as a light, except it's the opposite. So I'm not illuminating the scene with a specific wavelength. The scene is fully illuminated, and I use my filters to capture only specific band within that scene, and then I would rotate that to go to the next wavelength. And when I've collected all 5 of them, I have my multispectral images basically. So as you can see, a lot of those are not necessarily suitable for aerial imaging. I would say that the sensor-based one, the filter-based one is probably the best one. But this is what I'm going to be getting into after that, actually. So the rotating wheel, because you move the wheel in between capture, and then you take one more image, it's subject to the same problem I had before with my rolling shutter, is that the image, the scene will change. There's movement, the scene will change. So not quite suitable unless you can actually have a static scene. Using filter instead on cameras, which is the one at the bottom, you can now capture everything in one scene, but you need multiple cameras. That's actually a better way though to do that, because in this case, you just have to synchronize your cameras when you want to capture an image. And then you do get a scene, multiple images from one scene that were all captured at the same time that you can recombine after the fact. So that's actually a much better way to do multispectral imaging for aerial imaging application. Finally, when it comes to camera trends, thermal imaging. Thermal imaging has been around also for a while. We're looking here at long wave infrared. So when I was looking at that spectrum earlier before, you would see like UV, you would see visible, and then you would see also NIR. If you keep going, you're going to get short wave infrared, and then you're going to long wave infrared. Long wave infrared, that's also what's known as thermal imaging. It's been used in different applications too. It's been used in military application, obviously. It's been used in industrial applications. If a machine becomes too warm, it may be a sign that maybe there's something wrong with the mechanics behind it. So it's one way to do maintenance of mechanical equipment. It's being used in healthcare. Actually, it's being used with COVID-19 for fever detection. So those are thermal cameras. The problem with thermal cameras has always been the price. Those were pricey, and that was actually limiting the applications for those. But things have changed now. So the technology has become much more affordable. You see a lot more thermal imaging being done now outside of the military. I was talking about fever detection or just basic surveillance. There's basic surveillance cameras that do thermal imaging now. One company which is strong in that domain is FLIR. So that's a company we just purchased recently. We already had some offering in our portfolio when it came to thermal imaging, but with the acquisition of FLIR, we really expanded that. With thermal imaging, when you look at the camera, you also have to look at the optics. Those need to be precisely matched for your applications, so they go hand in hand. So that's something to remember. Connectivity can be somewhat similar to machine vision cameras. You can now get thermal cameras on GIGI, on USB, or even a direct digital output to connect into your own design, I guess. The key thing is that you're not only collecting those thermal images, you're also collecting metadata from the scene. So you have to be sure that this is supported, because in this case, you have to have information about the setup of the cameras being relayed to you with the image itself. So what are the key trends? Actually, a lot of those are similar to what you just see in the world of electronics. Things are getting smaller all the time. Sometimes too small. The phones kept getting smaller for the longest. Now they're getting bigger now. So smaller physical size. That's important because it does enable more applications. A lot of aerial imaging before was actually full-blown aircraft, and then larger UAV, and now you get very tiny consumer device, where you can also do good quality imaging on those too. Low power with CMOS, the use of CMOS. When I was talking about camera technologies, especially when I was talking about resolution from a few years back, those were CCD cameras. And the cameras today, they're CMOS. That means they're also lower power, which is another key benefit if you're going to be limited in your system because you're flying a small UAV, you have only so much. So to be low power is important. Low power, low weight, low cost. Electronic is what it is. Things only keeps getting cheaper and cheaper for the same level of performance. Let me clarify that, because sometimes there's misunderstanding around this. So new technology becomes cheaper. Old technology becomes more expensive. We keep selling our cameras for a really long life cycle. We sell products today that we introduced 15 years ago. That's not what you see with consumer devices. In our case, though, because of the type of applications we do, that's something that we have to do. So we make design decisions when we design products based on that we're going to have to have a long life cycle. Those cameras now, strangely enough, don't get cheaper over time. They get more expensive. As manufacturer of semiconductors introduce, let's say, new memory. Yeah, the new memory is bigger, it's cheaper. The old one, they were selling you last year, if you still want to buy it or if you can still buy it, goes up in price. So it's lower cost as long as you move to newer products. If you keep buying the same old products, most likely the price is going to be increasing actually. And finally, the other key trends is AI, artificial intelligence. That's a hot topic. I'm going to be talking about it more a bit later. Markets, trends in applications. We see more and more precision agriculture. We see more and more applications for infrastructures like bridge, rail inspections. Those type of things that more people are doing now. Those are things that people were talking about some years ago. I was one of those that was talking about these things, and now we're seeing it now. It's happening now. Geospatial mapping too, military application for that, mining application for that, so all kinds of different applications there too. So those are the key trends that we see, and it's a race. Like it keeps going and going. But the one I wanted to talk a bit more about is AI. So when it comes to AI, we're talking about AI because it's real now. I started my career many years ago, and at the time there was talk about artificial intelligence, and there was some other names for it too. I think it goes back to the 60s or something like this, when people were first talking about smart computers and stuff, smart machine and robot doing their own thing. And these trends came and went away. Maybe they overpromised and they under-delivered, and it was not possible at the time to do something really useful with the technology that was around. It's not the case anymore. That's why now we can talk about AI, and it's going to be in our life for a long time. The other reason to talk about AI is also because it's one way to innovate. A lot of products look the same. Cars, the same thing. Like if you want to buy one of these SUVs, they all look the same. You see that more and more. Like products now are designed based on spec sheets from what everybody else does, and you just try to do the same thing. AI allows you to differentiate your product, allows you to do something in a way that other people don't do that or cannot match that. So companies like ours see that as a key investment area where we can bring a lot more value to our customers, and you can do the same to your customers using AI to improve the capabilities and value of products. And it's everywhere. So yes, unmanned system for sure. I was talking earlier about all the things we do at TELEDYNE, and traffic applications and life sciences application, like counting cell in a blood sample, for example. AI can do that. So AI is everywhere. When it comes to AI, you might have heard or even used yourself image processing. People have been doing image processing for a long time. It just was not AI based. It was rule based. It's like writing a piece of software. You write a piece of code. Those are the rules. If this happened, this is what you do next. That's the traditional image processing. It's been around for a long time. With video, I used to do DSP baseboard frame grabbers many years ago. So that's what it was. So image processing has been around for a long time. Came from the world of DSP and signal processing. AI is different, often trying to achieve a similar result, but in a very different way. AI actually has proven it can deliver better result than image processing under certain conditions. I think both of them have a reason to be. If your system has a very well-defined set of rules, it's quite possible that traditional image processing might still be a better choice. If you don't, if things keep changing all the time, my first experience with AI was with a traffic application, and we tried to do something, vehicle detection and NPR and counting, all these things. for congestion pricing applications. So outdoor, within the city, there's cars on top of each other, there's rain, there's daytime, nighttime, cloud time, rain, snow, all these things. And it proved to be very hard to do that with image processing. We eventually gave up doing it. Like I think we reached an accuracy like the best we could do with traditional image processing. So defining the shape of vehicles, defining like capture area within the scene. I think the best we could do was maybe 70% accuracy, which wasn't good enough. And with AI, we're able to increase that to maybe close to 90%. So this is the type of things where AI is useful. When it's a complex scene, things are not easy to define. They keep moving around. This is the benefit of AI. So in aerial imaging, same thing. Like you can use AI for in the same way. One thing about AI that is important, though, even though AI is a software thing, you're training a system software-wise. It's a neural network most likely behind it. It still has to run on hardware. So what hardware are we talking about? Well, there's different type of AI. You have AI that can run at the edge on a host. Very different. On the edge would be actually on a drone. That's something I would consider at the edge right now. So you have a small embedded processor of some kind. It's most likely based on a GPU of some kind or an ARM core type of things, and you connect your camera to that processor board. That's edge-based AI. Host-based AI is a desktop. Could be a server blade or something like this, but that's more like a server or host type of machine. Those keep evolving quickly, even more so when it comes to edge-based devices than host devices, but those change too. When it comes to edge-based devices, we've seen the evolution. We started with FPGA-based, so field programmable gateway-based solutions, moving to GPU. And by the time we take a year to finish something, next thing you know is that NVIDIA has released the latest GPU. So when you design your system, that's something you have to take into consideration. If you're going to use AI, you have to think hard about the hardware platform for a couple of reasons. One of the reasons is that it's going to be changing. So whatever you design today, you might find that next year could work better if you are going to support the newer platform. So when you do a design, make sure it's platform independent. You don't want to be stuck into a very specific hardware, because otherwise it's going to be hard for you to benefit from the evolution of technology. The other reason is just the ability to purchase technology. A lot of those GPU and processing platform don't stay around very long because they get so good so quick. The life cycle is very short. So if you're going to be designing a new system on something, you want it just like as we do often. We want it to be able to offer for 10 years. That's the thing you have to take into consideration when you make hardware decisions. I can give you an example where when it comes to NVIDIA, of all the GPU products they have, I think they have a few. There's a small selection of those that are flagged as industrial, which means that they got to be supported for more than 2 years. Maybe not 10 years yet, maybe more like 5 years. It's already better than 2. So that's the other thing you have to worry about when you design a brand new system. Using AI is the hardware platform and how long it's going to be around. So when it comes to edge AI, the benefit of doing something at the edge, you can do something much smaller. Is because you can process the data right there. So you can, right at the edge, decide which data you're going to keep and which one you're going to throw away. Without that ability, you have to collect everything. So everything has to be designed to handle the worst case. So everything. So your interface, your storage capabilities, your processing capabilities of your host, everything has to be designed to support the full set of data. That can be expensive to do, and it might not be required to do. This is where Edge AI come in. So if right at the edge, you could make a decision on, listen, this one I don't need. Maybe I captured something equivalent the last 2 images, and for the next 10, I don't have to, I'm gonna keep going. So being able to make decision at the edge like this allow you to build a much more cost-effective solution, so a better solution overall, much cost-effective, easier to work with. So a lot of good benefits. That's why there's so much work being done right now around Edge AI. Quickly, if I look at some of the technologies behind it, I did talk about NVIDIA already, but there's other choices. It's not the only choice. Raspberry Pi is another choice that is getting better. We've been experimenting with the first one, wasn't good enough for the type of things we do. They're up to 4 now. The new one, Raspberry Pi 4, is actually a very nice, very capable machine that can really be used for hardcore industrial type of work. So something to keep in mind, actually. FPGA-based solutions too, they've been around. I think I did mention that that was one of the first experiments we did, was with FPGA-based solutions. And Xilinx is probably the best known one in this case, but there's other ones. And basically what they do is that they put right on a chip capabilities, including a GPU-like capability, but more than that. So there's also CPU-like, like ARM-based. There's connectivity as well. There's interfacing possible too. So there's multiple capabilities combined into an FPGA, which makes it interesting. But the problem is just that you're more bound by the actual hardware design itself. So the next slide, I want to get into an example, a case study of something we've done. Because currently we talk about all kinds of different technologies, but what does that mean, and what is it in real life? So we did get involved with some NDVI type of solutions, so multispectral imaging. NDVI itself started as a technology, I think, for satellite imaging way back when. It evolved, became applied now to multi-camera based systems, even to single cameras. You can use NDVI with a single camera. And this is what I'm going to be talking about as I go through the case study. So first of all, what is NDVI? It's just an index. What is an index? A number. It's just a number -1 and +1. The number is used to tell us about how healthy is a plant. So it can be used for agriculture, can be used for forestry and things like this. Number goes from -1 to +1, and if your result is between 0.2 to 0.8, the plant's healthy. So what does that mean? How does that work? Well, we know that a plant absorbs red light when it does photosynthesis. We also know that a plant reflects an IR light. So an IR light that hits the surface of the plant just gets reflected. That is only if a plant is healthy. If a plant is not healthy, it doesn't do so well. Maybe it doesn't absorb red light as well. Maybe it doesn't reflect an IR light too well. So if a plant is not healthy, something's going to be off a bit in how it does that. How do we translate that into an index? Well, that's the formula below. So that number is very simple. I take measurements. So if you go back to my multispectral way of doing things, I measured a specific wavelength. So in this case, I measure at only 2 wavelengths. I take one measurement in the red, and I take one measurement in the NIR, and I apply this formula to my measurement, and the number that's going to come out of that is going to be my NDVI number. And like I said, if that number is between 0.2 and 0.8, my plant's healthy, and if not, well, that's a problem. So this is what is NDVI. If I try to illustrate that in a different way, the plant is green. So why is it green? Because it absorbs red light through photosynthesis, and it reflects an AR light. If a plant is yellow, it's not healthy. Well, if it's yellow, it's dry, it won't absorb the red light in the same way. It would probably absorb an error at that point in time. So it's that simple. That's a way to translate that into a number that I can feed into my computer, basically. I don't have to do necessarily that with NIR though. So the issue with using NIR to do NDVI is that it's a bit more difficult to capture NIR. You have to have a special sensor to do that, or there's some sensors that do have some NIR capabilities, but they're not very strong. Actually, if you look at the curve in the middle, is the responsibility of a camera for different pixels. So a camera has 3 pixels, a color camera has 3 type of pixels, red, green, and blue. And that's the responsibility of these pixels. So when the red pixel is hit by a red light, it's going to translate those into an electrical signal, and that this curve is showing me how good it is at doing that. You can see that toward the tail end of the curve, which is where NRI is, I don't have a good response. So it's very, very weak. So maybe I can still use such a camera to do some NRI measurements, but it's going to be hard. So that's the problem with NDVI. So there's a different way to do that, which is called pseudo with NDVI, which instead of using NIR to do the measurements, use the blue. Now, my camera responds much better to blue than responds to NIR. So basically, using the formula right here, which is the pseudo NDVI, I can get a measurement which is as useful as NDVI simply by using a color camera. So I can use a color camera and the filter technique I was talking about earlier. So what I do is this curve on the left, which is my filter. So I would combine my color camera with a dual pass filter, and those commonly exist. They come in kind of different configurations. You can even custom design those if you wanted to. So this filter here has 2 wavelengths that it lets go through. Everything else is blocked. So there's one in the blue and there's one in the red. If I put this filter on top of the camera in the middle, the response of the system is the last curve on the right. So with this camera equipped with this filter, if I take a measurement, this is what I'm gonna get. I'm gonna get response in the blue, response in the red. I can combine 2 into this formula to give me an NDVI response. And I have a very simple system now to do NDVI measurements. Very simple, very cost effective. The other way to do that is with multiple cameras. And that's an example here. In this case, there's actually 4 cameras in that solutions. You could combine an RGB camera with a model camera for NIR response, or you can have 4 model cameras with specific filters for given wavelength, give you 4 different multispectral band. I was talking earlier about how cameras are small now. So because cameras are small, you can actually build a fairly compact systems this way. And the only thing you have to do after the fact is recombine the 4 images from the cameras. First of all, you make sure that they trigger at the same time, which cameras are pretty good at doing that now. And you have a piece of software to recombine those, so some kind of data fusion type of software, and you get your solution. Often these systems will also include a thermal camera. So I was talking earlier about thermal camera. This is where they come into play. So you get your multispectral imaging solutions plus a thermal view of the scenery you're looking at. And this is a real system. This is the aircraft, and it's flying it's for agriculture. So it's flying over fields now. And that's actually what comes out of it. You see it's colorized. And if I look at the first image on the left, actually, the first part is the visible image, and you look at the results after the NDVI calculations. And it's not obvious when you look at it visually speaking, but when you look at it with NDVI, you see that there's problem areas. The one in red are problem areas. Most likely it's probably too dry. It's too dry. You don't have to water the whole field now because you see that, oh, it's too dry only in this section. So you can be more efficient and you use your resource, water in this case, because you can only treat the part of the field that you have to treat. So that's one great benefit of NDVI. It applies to other things too. Plants can be unhealthy for different type of reasons. Each type of plants too might need to be tweaked. Corn doesn't respond the same way as some other produce. So these equations often are tweaked a bit depending on the type of crop that you're looking at. And the image analytics is a key part of that type of solutions. Just to conclude, these are the applications for multispectral imaging power relevant to agriculture. So you can fly things in high altitude, but people don't even fly drones within a greenhouse actually. So there's more and more applications using multispectral imaging combined with robotics for picking, for weed removal, just to monitor how your greenhouse is doing or how your field is doing. So it's quite exciting. A lot of things happening, a lot of new things happening. And that's all. That's all from me today. Any questions?
All right. Well, thank you, Danny. We appreciate the information and insight that you share with us during your webinars. If you know, for the audience, if you do have any questions, you can contact us, or you can reach out to Danny directly, and he'll be more than happy to chat with you about any of the information that he shared with you today.
Thank you very much.
Thank you. All right. Bye. Again, we appreciate Danny and TELEDYNE as the sponsor of today's webinar. We do have some upcoming events that are taking place that we'd like to share with you from BVI International. We do have our International Fuel Ethanol Workshop and Expo taking place in Des Moines in mid-July. We also have the National Biomass Summit and Expo and the Biodiesel and Renewable Diesel Summit. Probably the most relevant event that's taking place is the UAS Summit and Expo in Grand Forks, North Dakota, taking place in October. And that summit is shaping up to be a really good event this year. We were virtual last year, but it will be live this year. It is in its 15th year, and there's a lot of good things happening in the upper Midwest, primarily in North Dakota specifically. So if you can make that, we definitely want you to check that out at our website. And with that, again, we appreciate you being on, and this video will be recorded and we will post it online as well, so you can go back and check out any information if you did miss it. So again, thank you for being on, and we appreciate you attending our UAS Magazine webinar series and being a part of it. Thank you very much. Have a great afternoon.